Let's start with a very interesting question, children, over here. What we are into prove that sums. As we have discussed earlier, that when two prove that sums are there are two ways to prove it. So this being the very first sum, right, I'm going to prove it by both the ways. This is the very first sum of two proof. So I'm going to prove this by both the ways. Thereafter, I prefer K method. Now, one advantage of K method, you will be getting your answer very easily. Right? One disadvantage, sums are going to be a bit lengthy. As you will be seeing here itself, K method sums are going to be a bit lengthy, but the advantage is that you will get answers very easily. Right? So let's understand here K method, without K method, what's the difference? Then it's your call. Whatever you want, you can take it from your end and prove it. I shall make you understand both the ways. If A, B, C are in continued proportion, so given to me that A, B, C are in continued proportion, I intend to prove dash equals to dash. So let's start with our answer. Given to us, since A, B and C are in continued proportion. Mind you, I'm writing CP. You will not write down continued proportion as CP. I'm writing it shortcut as such. A, B, C are in continued proportion. Therefore, can I say A by B is equals to B by C? Which implies, which we have learned many a times, B square is equals to AC. Let this be my equation number 1, which implies B square is equals to AC. Right? Now, it's your call totally. It's totally your call whether you want to take LHS and move on to RHS, or you can take RHS and get proved LHS. I'm taking my LHS and trying to prove my RHS. So let's start with LHS. So what is our LHS? LHS is nothing but AB plus BC plus AC, the whole square. That's my LHS. Now, one thing should be kept in mind, that with ABC in continued proportion, what I have, B square is equal to AC. That means at times I can replace B square by AC and vice versa. AC can also be replaced by B square. Let's start. AB as it is, BC as it is. Do I have AC? Which I shall replace by B square. B square. The whole square. From where did I take this value? I shall write down from equation number 1. Right, children? I just replace this AC by B square. Now what? What do I see? What do I see from all the three terms? I do see that B is common. Shall we take B common? B common. Thereafter, mind you, this is the whole square. So if you want, you can say with a bigger parenthesis, the whole square is intact. The whole square is intact. B is common from all these three terms. I am left with A plus C plus B. Right? Now I look at my RHS. Are we done? Let's see. We do have A plus B plus C, but I just have A plus B plus C, the whole square. And AC, no, that's separate. As of now, I'm having B common, A plus C plus B, the whole square. Arrangement can be done, A plus B plus C. As of now, we are having A plus C plus B. Arrangement can be done. This square is applicable to the smaller parenthesis. At the same time, it is applicable to B also. So what I shall say, B square with arrangement A plus B plus C, the whole square. This square is applicable to B also and the inner parenthesis also. Now at least I have the first part. What is missing? Sir, here there is AC. What you have is B square. No problem. B square is AC. So again, AC, A plus B plus C, the whole square. Once again, from where did I get it? From equation number 1. If you check, that's what our RH is. Since LHS is equals to RHS, therefore, we write down the entire question. Therefore, the entire question is AB plus BC plus AC, the whole square is nothing but AC into A plus B plus C, the whole square. We are done. Right? So short the sum is going to be? Indeed yes, so long as you go without K method. Now method number 2. K method, slightly big. What we are going to use is, we are going to use the basics what we have learned in just previous slide. What we are supposed to do when it's K method. First, we are going to write down, it's given to us that A, B, C are in continued proportion. So same lines, since A, B and C are in continued proportion, therefore can I say by K method, A by B is equals to B by C, which is equals to K. Refresh your concepts, refresh the slide which we have learnt, where K is any non-zero constant, where K is any non-zero constant. What? Extreme right. Therefore, B by C is equals to K, which implies B is equal to CK. Equation number 1. Also, A by B is equals to K, which implies A is equals to BK. A is equals to B is CK, CK dot K, CK square. Equation number 2. This is what we had learned earlier in the previous slide, and this should be there in every single sum. Mind you, in exams you have only one question, right? So here we are going to go for multiple questions. While practicing throughout the year, you will be practicing multiple questions, around 20 sums. So every time you might be finding it tedious, boring to write down, but in exam we have to write down only once. So please don't make any shortcuts. Thereafter, once this is done, we take LHS. So our LHS is, what is LHS? AB plus BC plus AC, the whole square. AB plus BC plus AC, the whole square. Henceforth, wherever we have B, we are going to replace it by CK. Wherever we have A, we are going to replace it by CK square. And what about C? C is going to remain as it is. So A, it is going to be CK square dot B is nothing but CK plus B, which is CK dot C, nothing. A CK square, the whole square. What next? Can I say C into C, C square K cube plus C square K plus C square K square, the whole square. What shall be taken as common? If I arrange it, C square K cube, C square K square, C square K, the whole square. Can I take C square K common? The whole square will be there. C square K common. I'm left with what? C square K common. I'm left with here K square. Here C square K square. C square K common. So K square plus K plus C square K common 1. The whole square. The whole square. So this square is applicable to both. I shall write down C raised to 4 K square and K square plus K plus 1. The whole square. This is what my LHS is. This is what my LHS is. This is our LHS. I think so. Here is what I'll take it. Individual square, parenthesis closed. This square belongs to this also. This square belongs to here also. I need to say this square here. C raised to 4 K square plus K plus 1, the whole square. This is my LHS. Let's solve RHS. What is our RHS? RHS is AC, A plus B plus C, the whole square. So wherever there is A, we are going to replace it by ck square dot c. Next, what is A? ck square. What is B? ck. What is C? C, the whole square. C square, k square. From here, can I take C common? K square plus k plus 1. This square is applicable to this parenthesis at the same time C. C square, k square. This square belongs to the C also, so C square. And then k square plus k plus 1, the whole square. Now, what? C square into C square, C raised to 4. K square plus k plus 1, k square plus k plus 1, the whole square. C raised to 4 k square plus k plus 1, the whole square. C raised to 4 k square plus k plus 1, the whole square. This was my LHS. Let me say this is equation number, we are done with 1, 2. So let me say this is 3. This is our RHS. We are done with this. Let me say this is equation number 4. From 3 and 4, LHS is equals to RHS, and we can write down thereafter the entire question. Finding a bit difficult, but I think so. It comes to easy when sums are a bit difficult, K method becomes an easy way to solve it. Right? Even if you can solve it this way, there are many in the very first sum, there are many who might go with this. So this is quite easy. Believe me, when you practice more sums, you will find this one more easier. Depends upon student's choice. Whatever is your call, you can take it.